Hello everyone, in this video I'm going to be going over heating curves. So this one is going to be, practice questions might be a little bit tougher because we have to deal with multiple different equations and we have to decide when to use the equations, and we're also going to be using Google a lot. The reason why we're using Google a lot is because we need to find the specific heat and the heat of fusion and vaporization of different chemicals. So with heating curves, we will be given that information on the test. We're not expected to memorize anything like that, so just keep that in mind, that while we're working through these, although I'm Googling them, you're not expected to know them. They will be given on the test. Okay, so heating curves. Heating curves show us the temperature with respect to heat added. So when we say that, that means that in the graph we can see different phases that occur at different temperatures according to, or at when different heat is being added, and that'll tell us the temperature where those phases are occurring as well. So let's look at the graph right here, right? So here's an example of a heating curve. There's no specific temperatures mentioned or heat added, so this is just to give you a general idea of what they'll look like. So we see that the curve, it's not really like a curve. You know, when we think of curve, most often we're like, oh, that's a curve. This type of curve is just a graph that has a shape to it, right? That's another way to describe a curve. But this curve, you have a positive slope and then a zero slope, so that it's not sloping up. My picture's not perfect, so there's a tiny bit of a slope there, but it's supposed to be flat. Then we have another positive slope, and we're going flat once more, and then finally another positive slope that will continue to go up. So what these different slopes and everything mean is the slopes that have like a number to them. So let's just say like the slope of this is 1 or something. Either way, if it has an incline and it's increasing, so the temperature is increasing, we can say that's where our phases are occurring. So that's where we have our solid, our liquid, and our gas. In these spots, so I'll like highlight them. Do I have like a highlighter? Maybe I'm just not looking good enough, but I don't see a highlighter, so I'll make a highlighter. Okay, so in this phase, and in this phase, and in this phase, these are all going to be just our general phases, and within these, what's actually occurring is just the temperature is increasing, right? So you have a liquid. Let's say that you have water, and you're heating that water from 20 degrees Celsius to 50 degrees Celsius. That's all occurring in here. Nothing's evaporating, nothing's melting, nothing's freezing. It's just staying in this liquid phase. Same thing with a gas. The thing is already a gas. You're not going to change the phase of it. All you're doing is increasing the energy, which is also increasing the temperature by adding heat to it. Solid, same thing. Let's say that you leave your phone out on a hot day, it overheats. What's occurring there? Your phone isn't melting. Your phone isn't evaporating. Your phone is just simply getting hotter. So the temperature is just increasing. You're not changing the phase. Now, let's take a look at these other phases here. This one and this one. What's occurring in these phases is actually a phase change. So, all of the heating curves where the slope is 0, so where the temperature is not changing, that is where your phase changes are happening. So here we have our solid to our liquid to gas. It's always going to be solid, liquid, gas, because unless you're dealing with sublimation or deposition, but most often your heating curves will have your solid, then your liquid, then your gas, with phase changes in between the two, or 3, I guess. So first thing is, why doesn't the temperature go up within a phase change? It might kind of make sense if you're that the temperature would change, but it doesn't change. The temperature is actually staying 0. And the reason for that is because all of the heat that you're adding is going into changing the phase, right? So your molecules have to use all of the heat to become excited. They need to move around and move around and move around and move around until they change their phase. So that requires a lot of heat. So all of the heat that is being added is going towards that changing of the phase. You're not increasing the temperature. You're not decreasing the temperature. The temperature is staying 0 because it's putting all of its energy into changing the phase. So with that being said, we do have some equations that we're going to be working with as well. When we're computing these things, right? So the first one is Q equals mc delta T. There's many different ways to write this. I think Professor Sherlock tends to go for Q equals specific heat times mass times delta T. They mean the same thing. C is just representing the specific heat, so these two mean the same thing. But that's just the way that I write it because that's the way that I was taught how to do it, and that works for me because Q equals mcat. I don't know, it's an easier way for me to memorize it, I guess. So, in this equation, the Q is your heat, M is mass, C is specific heat, which can change per phase. So there's a specific heat of water when it's a vapor. There's a specific heat of water when it's a liquid, which is 4.184 joules per mole or something like that. And then there's the specific heat of it as a solid or as ice, right? So that will change per phase. Again, that will be provided on the test, whatever question we're dealing with. And the change in temperature is always going to be your temperature final minus temperature initial. Just a reminder with temperature final minus temperature initial, it doesn't matter if you're in Celsius or Kelvin. The reason being is because when you're subtracting them from each other, so let's say we're doing 0 to 10 degrees, that's going to be what final is going to be 10 minus 0 is just going to be 10, and then converting that to Kelvin, we have 273 minus 2 or 2 not minus to 280, so 280 is your finals, 273 is your initial. It's still going to be 10 degrees, so they're interchangeable in that way. So it doesn't matter which one that you do. I find Celsius easier to work with because it's a lot less numbers, and usually you're working with like a 0 in there or something simple like 10 instead of 273. So I find that one to be a little bit easier. And you're going to be using your Q equals mc delta T when you're dealing with no phase changes. So when you're staying in a phase, so when you're going from, let's say this is like 20 degrees to 50 degrees, that's when the Q, or the heat added, is going to be equal to the mass times the delta C, or times the C times delta T. So that's when you'd be using that equation. So the next one is Q equals delta Hn, where Q again is heat, so that heat added, and delta H is going to be your change in heat per mole, and the change in heat per mole differs for every single different compound, and it's also going to differ between if there are going from a liquid to a solid or a liquid to a gas. So your heat of fusion is when you're going from a liquid to a solid, or solid to liquid. One's going to be negative and one's going to be positive. And then your heat of vaporization is when you're going from a liquid to a gas or a gas to a liquid. It's going to be different for every single thing. Again, you can think of it as like if you leave a bottle of water out, it's going to require not that much heat to be added in order for it to evaporate versus your phone. Your phone's not going to melt, so they have different heats of fusions and different heats of vaporizations. And then the next thing is N, which is going to be your moles, right? And that makes sense because we're dealing with the change in heat per mole. In order to find heat, we just have to multiply it by moles to get rid of our moles, and then we find the heat added. And we're going to be using this during our phase changes. So that's why we use heat of fusion and heat of vaporization, because here we're changing our phases. So that's when we'll be using them, is during our phase changes. So the ones that have slopes that are increasing is going to be your Q equals mcat. And then the next one, we're going to be Q is equal to delta Hn, and then we're going to back mcat, delta Hn, mcat. So that's just something that you should keep in mind. So let's work on a practice problem. So here's our heating curve practice problem. So filling out the chart. So from A to B, B to C, C to D, D to E, and E to F, which are marked by these points here, you're going to tell me what phase it is in. So this segment here is going to be your A to B. This will be your B to C, your C to D. You're going to tell me the phase that it's in. Either it's going to be in a stable phase, so it's going to be a solid, liquid, gas, or it's going to be changing phases. So you would say solid to gas, or not solid to gas, solid to liquid, liquid to gas. You're also going to fill out what is happening to the temperature. Is the temperature increasing? Is it decreasing? Or is it not changing? And then which equation will you use to find your Q? So if you want to go ahead and fill that out, this will just help you with the concept of heating curves. I'll fill it out now. So from A to B, we are in the solid phase, and the temperature is increasing, and we are going to use Q equals MC delta T. B to C, we are going from a solid to a liquid, so the temperature is not changing, and the equation that we're going to use is Q equals delta HN. C to D, we are in the liquid phase, and all we are doing is increasing the temperature, so we're going to use our Q equals MC delta T. Then D to E, we are in the, well, we're actually changing phases, so we're going from liquid to gas, so the temperature is not changing, and again, when the temperature doesn't change, we're going to use our delta HN. And then our last one is from E to F, where we are staying in the gas, and the temperature is just increasing, so we're going to use our Q equals MC delta T. Alrighty, let's move on to some practice problems. So the first one says, what amount of energy is required to convert 1 mole of ice at negative 50 degrees Celsius to liquid water at 70 degrees Celsius? Okay, so I actually have a good tip on figuring this out. I actually learned how to do these over in Physics 2. So you learn it first in Gen Chem 1, and then you go over it again in Physics 2. So having that background has been really helpful, but my way of doing this is what I like to do is I like to write out all the phases that are happening, right? So I like to do it out in steps. So the first step for this one, so we're at 50 degrees Celsius with ice. This will be provided on the test, and if it might not be provided on the test, but it's something that we should keep in mind, that water will go from a solid to a liquid at 0 degrees Celsius, right? And we know that. That's when ice will melt. And then water will also go from a liquid to a gas when it boils at 100 degrees Celsius. So I'm just going to keep that in mind here. So the first thing is we are bringing the ice from negative 50 degrees Celsius to where it's going to melt at 0 degrees Celsius. So that's our first thing that's happening. I'm going to write that this is ice so that I know when I'm finding my C value. And then the second thing that's going to happen is going to melt. So that's the next thing. So we're going to say it's going to melt. And I'm going to write that it's 1 mole of it. Okay, and then the third thing, now that it's in the liquid phase, actually, let me write this in here. So it's going to go from a solid to liquid, just so that I have that in my mind in case I forget what melting means. So now that we're in the liquid phase, we're going to go from 0 degrees Celsius to now 70 degrees Celsius. And we are staying in the liquid phase. Okay. Cool. So now that I have those things written out, I know I'm going to have to do 3 separate equations, and then I'm going to add all those things together, right? So for our first equation, when we're dealing with a temperature change, we're going to do Q is equal to MC delta T. So we have to find our mass, actually. So we know 1 mole of water divided by 1. Apologies for my dog. 1 mole of water, there's 18 grams. So we're going to have 18 grams. let me just shut my door real quick because my dog is barking. So we have 18 grams, so that is our mass. So we have Q is equal to 18 grams times our C. So let me find specific heat of ice. Okay, that's a large number. I don't want kilograms, I just want grams. So let's say grams C. Okay, 2.3. So we'll use 2.03. That's correct. What does it say here? Per gram degrees Celsius. Okay, cool. Okay, and then our change in temperature, we're going from negative 50. Okay, so it's gonna go because we're doing final minus initial, so we're gonna make it into a positive. Okay, so doing that out on our calculator, it's gonna be times 18 times 50, and we are going to get a Q of 1,827 joules. Our second phase, we're going to be going from solid to liquid, so I'm going to have to find the heat of fusion. So heat of fusion of ice. Okay, so heat of fusion of ice. Yeah, okay, so 333.55. Okay. So, alright, we're going to use this equation, delta H, and we'll use N. So our N is just 1, and our delta H is 333.55. So our Q is going to be 333.55 joules. And then for our third thing that's happening, we're going to be increasing the temperature of the liquid. So our Q equals MC delta T. We're keeping the same amount of moles, so we'll still have 18 grams. The C for water, I know off the top of my head, is 0.4184, but let me check it. What are they gonna? Okay. Specific heat of water. Kilocalorie. Yep, okay, cool. Always good to double check yourself, and here we are going from 70 degrees to 0 degrees. So doing that on my calculator, 18 times 70, oops. Hang on, let me just make sure I did that right, because I got a weird number. Wow, my calculator just hates me. It just deleted everything that I was just doing. 70, alright, cool. So I was right the first time. So 5,271.84. Okay, and now what I'm going to do is I'm going to add all of these together. So I'll add all of these. And I got 7,432.39. Now let's bring that into sig figs. This is also in joules, so I'm going to convert it to kilojoules. So we'll get I'm going to go to 2 sig figs, 7.4 kilojoules, and that will be your answer. Let's check it. He got 13.16, which is not what I got. One more ice. Oops, all the way over here. Interesting. I wonder what might have gone wrong. For some reason I want to assume that it's this. I just feel like this heat of fusion is wrong. Of ice. That's what it says. Joules per gram. Oh, we want joules per mole. Joules per mole. There we go. Okay. That's why we always want to check. This is a learning moment for me and everyone else here. You always want to check your units. So this is going to actually be 6,000. I was like, I feel like it's more than that. Not 6,005. It's gonna be 6,000. Actually, I want to say it is actually that, but okay. So now let's redo this one. So we're gonna get a different answer here and here. Apologies for that. That was Google's fault for not giving me what I wanted. So this is still just gonna be 6,010 joules. Now let's add that to our 5,271.84 plus the 1,827. Much better. All right, there we go. So now we have 13,108.84. Again, sig figs, and we're going to convert it to kilojoules. We'll get 13 kilojoules, which is just about what he got. All right, that ended up being much better now that we fixed that. Okay, so that's all that I'm going to do for this video. I do have another practice problem, and it's just directly from the, the little study guide that he makes, but it's going through the same process, so I won't do this exact same thing again. But it's a good idea to practice these. I actually find these pretty fun. But yeah, so thank you all for watching, and yeah, have a good one.